Okay, this is the introduction to 12 chapters, a video series, which will show the high points of this book. Organic Chemistry Principles in Context, a Storytelling Historical Approach. The book takes an unusual approach to the teaching of organic chemistry to beginning students, and it's available on Amazon for $25. And this video series is going to pull out of each chapter the essential points of each chapter. So this is will be available hopefully on the web and also as discs. And it's intended to be used. What this video series is about is that it's intended to be used with the book. It's not a course in itself. It might be used for flip teaching, which you can find out what that's about on the web. And it's being presented by its author, that's me, Mark M. Green, with the help of Maxwell English, who you'll meet at the end of chapter 12, who's standing behind the video camera right now and taking care of all the editing details and technical details. Maxwell is going into his senior year in September at Greenwich High School in Washington County, New York State. The video will follow, therefore, as I said, does not constitute a year course of study of organic chemistry on its own, but does accomplish this purpose when used together with the textbook from which the video is derived. So this is an introduction to each one of the 12 chapters, but you're only going to see it once at the beginning of chapter 1. So let's get going now with chapter 1. From cellulose and starch to the principles of structure and stereochemistry. Cellulose and starch are both polymers, very large molecules, macromolecules, made by recurring units of glucose. Glucose is the most common organic molecule on Earth, the product of photosynthesis, the sun's energy working on carbon dioxide and water makes glucose. And we're going to discover that it's possible to learn the fundamental principles of structure and stereochemistry by looking at the structure of glucose in its various forms. And that's what I would like to begin with. Here's something called alpha-D glucose. We'll find out what that means later. The D. Beta-D glucose. These molecules are both glucose. If you look carefully at them, you can see that they're different from each other. This molecule and this molecule are identical, except for that oxygen and hydrogen, a so-called hydroxyl group, pointing downward here and pointing somewhat upward in that direction. Now, the first question we want to ask is, how do these pictures, these two pictures, correlate with the formula of glucose? Now, what is the formula of glucose? C6H12O6, which corresponds to C6H2O taken 6 times. That's why glucose is called a carbohydrate. Carbo, carbon, hydrate, water. So this is the formula for glucose. But how do these pictures correlate with that? Well, in discovering how these pictures correlate with that formula, we discover a fundamental principle of the way organic chemists present molecular structures, which is often by not showing all the atoms that are present. And we can see that expressed very well right here. For example, there have to be 6 carbons. Do you see? I don't see any carbons at all. There's not a single symbol for C in that structure. How about oxygens? Are there 6 oxygens? Well, 1, 2, 3, 4, 5, and 6. So the oxygens are shown by the symbol O. Are there 12 hydrogens? I don't think so. 1, 2, 3, 4, 5. There are 5 hydrogens. So obviously there are atoms missing, and what I've said here identically applies to the beta glucose down below. Well, the reason for that is that organic chemists often don't present all the atoms when they draw a structure because of something that's well understood. If you've got 2 lines in a structure like this coming together at an angle like that, then by definition there's a carbon at the intersection of those 2 lines. If we apply that rule, and that would be true for any molecular structure, we'd have to put a carbon here, and a carbon here, a carbon here, a carbon here, a carbon here, and a carbon here. And suddenly we get 1, 2, 3, 4, 5, 6. We get the 6 carbon atoms of the C6 in glucose. The other rule is that if you have 2 lines together and there's a carbon there, and there are no lines there, the carbon has to have 4 lines to it. Those 4 lines can take all kinds of different forms, which we're going to come across as we go through the course. But if there are no lines other than 2 lines to that carbon, there have to be 2 more. And those 2 more, by definition, have hydrogens at their terminus. So we have to put a line here and a line here, and put a hydrogen here and a hydrogen here. Now under these conditions, if we apply this rule to glucose, there has to be a hydrogen here, there has to be a hydrogen here, a hydrogen here, a hydrogen here, a hydrogen down there, and there would have to be 2 here. And if I've done everything correctly, then this should have 12 hydrogens around it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so by applying this simple idea, we end up with C6H12O6, C6H2O taken 6 times, a carbohydrate. You can do that for any molecular structure. I could do that for a very complicated structure, like here's, let me see if I can remember correctly the structure of cholesterol. I think that's cholesterol. Is it? Or maybe, I think maybe we have that group over here like this. There's an OH here. There's a line here like this. And if we apply this rule, every angle, there's not a single carbon in here. Every angle that comes together has a carbon. Wherever there aren't 4 lines, then there's 2 hydrogens. Here's a carbon that has 4 lines to it. 1, 2, 3, and 4. That's a double bond. We're going to come to that later. Here's a carbon with 4 lines to it. 1, 2, 1, 2, 3, and 4. Here's a carbon here with only 1 line to it, and therefore there has to be 3 hydrogens on that. So we're going to deal with that as we go along in the course. So in other words, this is the way that you draw molecular structures. You draw them without showing all the atoms necessarily. Sometimes you show them with some of the atoms. Sometimes you show them with none of the atoms. Sometimes you show them with all of the atoms. But when the lines are missing and angles come together like that, then we know by definition what belongs at that place. So now that's a kind of a nomenclature. That's a kind of the way we define the way the structure is written. But the really important and interesting thing about glucose or about any organic structure, including cholesterol, is what are these lines? That is the question that we want to ask. There are these lines. What are these lines? If we have a carbon with these lines, and maybe you've got another carbon here like that, what are these lines? That's the question that we want to ask. Let's now pay attention to that question. Let's erase this. What are the 4 lines to each carbon atom? Well, what does carbon look like? If we had an isolated carbon atom in outer space and it was in a relaxed state, all its electrons were there, then quantum mechanics would teach us that the electrons fill orbitals with increasing energy, or in one way of thinking, further away from the nucleus of the atom. The nucleus containing the protons that correspond to the atomic number of carbon. Atomic number of carbon is 6. There are 6 protons in the nucleus. Therefore, in a neutral state of carbon, there are 6 electrons around that nucleus. These electrons occupy a first quantum level where there's one orbital, the 1s orbital. There are 2 electrons in that orbital. The second quantum level, in which there's a 2s orbital with 2 electrons in that orbital of opposite spin. This is something you learn about already in high school, or certainly in general chemistry, and before you get to organic chemistry. Then we've got 2s, then you've got 2px, 2py, and 2pz. So these are the way the electrons are distributed. The way these electrons are distributed right now is, if we had a carbon like this and it was not bonded to anything, let's forget about the 1s orbital for a second and just talk about the second quantum level. The second quantum level is the so-called valence shell. It's the quantum level that's associated with the bonding of carbon. If we have here 1, 2, 3, 4, then in fact, if I represented this pictorially, in a representational way, I would have 2 electrons here, which I could show as dots, 1 electron here and 1 electron here. Now these lines that we talked about are covalent bonds. So the lines are covalent bonds, and a covalent bond involves an atom, let's say X and X, with the sharing of 2 electrons in that bond. If we wanted to make covalent bonds around carbon, and carbon was in a state like this, these 2 electrons are already shared. They exist in the 2s orbital. Here's an electron here and an electron here. If we wanted to make, for example, bring up a hydrogen, where hydrogen has 1 electron in the 1s orbital corresponding to 1 proton in the nucleus of hydrogen, then I could bring a hydrogen here, bring this electron up and that electron down. I could bring a hydrogen here, this electron up and this electron down, and this would give rise, therefore, to these 2 paired electrons in the 2s orbital, and a hydrogen here and a hydrogen here. Now it turns out that under rare circumstances and in a very advanced way, this kind of highly reactive form of carbon bonded to hydrogen can exist. But under normal circumstances, the common form of carbon bonded to just hydrogen is a molecule called methane. Methane has the formula CH4. Now how can you possibly make a carbon bonded to 3 atoms of hydrogen with the electron configuration in the valence shell in the form that it's in now? This led to the idea of hybridization, which is something that Linus Pauling is given credit for. What Pauling suggested is that making these bonds is an energy lowering situation, and that the energy given to the system by the making of those bonds makes energy available to reorganize the valence shell of the carbon atom. And that valence shell reorganization happens as these bonds are being made. But let's look at it now in a kind of independent manner. If we were to take the 2s orbital, 2px, 2py, and 2pz, and mix them together as if we were stirring a bunch of chopped vegetables in a pot. I mean, it's mathematically speaking, we're going to take all these orbitals and mix them all together in an intimate way. And since we start out with 4 orbitals, 1, 2, 3, and 4, we can extract out of that 4 orbitals. Each orbital will be identical. Each one will have 1 part of s and 3 parts of p. sp3, 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 and sp3. Now, since these orbitals will all have identical energies, we can put 1 electron in each of these orbitals. If we put 1 electron in each of these orbitals, then we come up with something quite different, don't we? Now we have carbon, dot, 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 and dot. Now we can bring our hydrogens with their opposite spins the opposite spin here and make ourselves a molecule of methane. And so things work that way quite nicely, and this hybridization picture works as described here for the tetravalency of carbon. This is a carbon which is tetravalent, but carbon can also be trivalent, and the valence can appear in different ways. Carbon can be carbon can be bonded to oxygen with a double bond, to carbon with a double bond, to carbon with a triple bond. There's all kinds of ways to bond that, and each will have their own kind of hybridization, and as we go ahead in the course we'll look at those. But right now let's look at carbon in a tetravalent state, which is, by the way, the situation in glucose. If you look at here's for example beta glucose. If you apply what I talked about, putting all the carbons and hydrogens in, every carbon atom in this molecule is tetravalent, and therefore every carbon atom in this molecule is sp3 orbital or approximately sp3 orbital, because strictly speaking it's only absolutely sp3 orbital if all the entities around the carbon are identical to each other. But for our purposes now it's good enough to call every carbon atom in this structure, which is all tetravalent, sp3 orbital. Now another thing is explained here. I don't know if you noticed this as I did this, but I'll make it clearer right now. I'm going to darken these bonds in the front here. I'm not darkening them because they're different from the bonds in the back. I'm darkening them because I want to emphasize that this is a three-dimensional structure. And in fact, if I translate that three-dimensionality into a molecule like methane, that this is not really a true picture of the three-dimensional character which methane is. Methane actually has the hydrogen atoms on that carbon atom pointing to the corners of a tetrahedron. And pointing to the corners of a tetrahedron, the fact that the methane exists not in 2 dimensions here, but in 3 dimensions, you can really see that in one way of thinking, although this is discussed in the book in a different way, and it's expected that you're reading the book in concert with this work, that we've made these hybridized orbitals out of px, py, and pz, and if we've made them out of px, py, and pz, well then it certainly has to be the case that these hybridized orbitals have to exist in 3 dimensions. And the 3 dimensions they have to exist in are the x, y, and z Cartesian coordinates. And so it's the use of the 3-dimensionality of the p orbitals in combination with the s orbital that is a foundation for the 3-dimensionality of methane. But there's another way of looking at this too, which is discussed in the book, and that is the fact that each of these lines has 2 electrons in it. Now the strength of the covalent bond is associated with the fact that these 2 electrons in that bond are attracted to the proton in the hydrogen, the single proton in the hydrogen nucleus, and the 6 protons in the carbon nucleus. It's that attraction between these electrons and that positive charge within the nuclei of the atom that makes the strength of those bonds. But there's a repulsion between the 2 electrons in any one of these bonds. And if you've got 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, attracted to the nuclei, making the strength of the bond but repelling each other, the way to get them as far away from each other as possible is in fact to have these bonds point toward the corners of a tetrahedron. If they were flat like that, then this angle would be 90 degrees. This angle is in the ballpark of 109 degrees. So we get, out of this hybridization picture, we get a nice correspondence to the 3-dimensionality of tetracoordinate carbon, and we also understand how these electrons in these orbitals in the valence shell, the second quantum level, can be mixed together in order to make the bonds that we know that carbon exists at. And here's this is all shown right here. Now let me erase this right now. I hope I don't I hope I don't louse this up. Okay, let's take this carbon and put it in the context of the other atoms in the second row of the periodic table that have their valence shell in the second row of the periodic table. To put them in context, we have to know their atomic numbers. Well, we know hydrogen has an atomic number of 1, and helium has an atomic number of 2. And now we have, in the second row of the periodic table, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. I hope I didn't leave anything out. Atomic number of lithium is 3, beryllium is 4, boron is 5, carbon is 6, nitrogen is 7, oxygen is 8, fluorine is 9, and neon is 10. Well, let's take this and not hybridize anything and just look at this. Where's lithium? Well, you have one s, 2 electrons here, and then in the 2s orbital, higher energy, further away from the positive nucleus, we've got 1 electron here. Well, how would lithium bond? Well, this has to do with the driving force for this bonding. The driving force for the bonding of these atoms has to do with trying to attain a noble gas electronic configuration. Lithium is closest to helium. If lithium were to give away one of these electrons, then we'd have lithium plus minus 1 electron, and that's the way lithium bonds. Lithium bonds as a positive lithium, and if it had to give away one of these electrons, where might it give that electron to? Well, let's look at fluorine here. Fluorine would be 1s, 2s, 2px, 2py, and 2pz. And the 1s here, we have 2 electrons down here, and there's 9 of these. 1, 2, 3, 4, 5, 6, 7, and that's 8. 1, 2, 3, 4, 5, 6, 7, 8, there's 9. Well, how would fluorine become, if lithium becomes more like helium, how would fluorine become more like neon? Well, if we take this and we made this guy red and turned it over like that and gave that red electron here, now we give away minus the red electron, we get lithium plus, and we grab an electron here, and now we get fluorine minus, and so we can make lithium fluoride. The fluoride now has 10 electrons just the way neon does, and the lithium is missing 1 electron, so it becomes just like helium. And we can play these games with all of these atoms. I don't want to go through all of them, I just want to go through some of them, which shows you the principle involved here. So these atoms are trying to bond up in a manner, are trying to bond in a manner to make them resemble the electron configuration of the noble gas helium down at this end, or the noble gas neon down at that end. Well, in that particular case, let's just go one more. Let's take beryllium. So beryllium is 4. So you're 1, 2, and then you've got the 2s orbital. Here's the 1s orbital, and there's 2 in here. What would beryllium do following the same kind of driving force as we had for lithium? Well, if it were bonding up with fluorine, it could give both of these, it could give one of these each to a fluorine atom. Let's do that. Let's put these 2 electrons up here and rewrite the fluorine. 1s, 2 electrons here, 2s, 2 electrons here, 1, 2, 3, 2px, 2py, and 2pz. And the fluorine has 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, that has to go in the opposite spin direction. Now, if we had two beryllium atoms, and so one of them would be here, the other one would be 1s like that, 2s, and this has 2 electrons in it. The beryllium is 4. How could we deal with this? We have the fluorine. We have the fluorine here. We have 2 fluorines, 1s, 2s, 2px, 2py, and 2pz. 2 electrons like that. 2 electrons like that. These are the 2 fluorine atoms. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, how could this be dealt with to satisfy the beryllium and satisfy the fluorine? Would we use 2 beryllium atoms? 1 beryllium for each fluorine, as we did for lithium? I don't think so. Because if we use 1 beryllium for each fluorine, then we could only give away 1 of these electrons, and the beryllium would still not resemble the helium. And so, in fact, we don't deal with two beryllium atoms. We deal with 1 beryllium atom. Take 1 of these electrons, red electron, and give it away here, and take it away from there. Take the other electron, and we can reverse its spin and give it away like that, and then we would make a beryllium with 2 positive charges bonded to 2 fluorine atoms. The overall formula, beryllium F2. And these fluorine atoms would then have 10 electrons, just like neon, and the beryllium atom with the double positive charge would just have 2 electrons, just like helium does. And we can see how carbon has done that. Carbon would like to have the electron configuration of neon. And it does that in this particular case. If we take a CH4, and there are 2 electrons in the 1s orbital here, and then we have 2, 4, 6, 8, and those 2 make 10, and then we have a carbon that's like neon. And if you play that game, now let's do that with nitrogen, because nitrogen is an interesting situation. If we take nitrogen with an atomic number of 7, let's get rid of our fluorine for a second. So if we take nitrogen with an atomic number of 7, we have 1s, 2 electrons here, 2s, 2 electrons here, 2px, 2py, and 2pz. 7, 1, 2, 3, 4, 5, 6, and 7. Now, how would nitrogen attain the electron configuration of neon? Well, it would have to make 3 covalent bonds and leave 2 behind. Well, in fact, the way that nitrogen bonds up that is through a hybridization pattern. Forgetting about 1s for a second, now we have 1, 2, 3, and 4, sp3, 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 and sp3. Formally speaking, we've got to share among these 1, 2, 3, 4. We've got to share among these 1, 2, 3, 4, 5. Well, 1, 2, 3, 4, and one of them is going to have 2 in there. Now, if we bond up, if we pair these 3 in here, then we can get a molecule like ammonia. And this is a hydrogen, and a hydrogen. And that would be sp3 to a hydrogen 1 electron, sp3 to a hydrogen 1 electron, sp3 to a hydrogen 1 electron, and 2 electrons in here, and this we call a lone pair. So because of the electron configuration of nitrogen, we have these 2 electrons left over, and we still attain the electron configuration of neon. Namely, 1, 2, 3, 4, 5, 6, 7, 8, and 2 in the 1s orbital make 10. So that's like neon. And if we play that game with oxygen, which is the element that we see that is so commonly found in in glucose, let's do that with oxygen. Well, here's oxygen, 1s, 2s, 2px, 2py, and 2pz. Oxygen has an atomic number of 8. 1, 2, 3, 4, 5, 6, 7, and we have a, oops, excuse me, we have a, sorry, we have here 2px, and we have 2 electrons paired in that position right there. Now, how would oxygen attain the electron configuration of neon, a so-called filled shell, the electron configuration of a noble gas, a gas that has essentially no reactivity, that's a very stable situation? Well, I would say that the oxygen has to bond up with 2. Well, first of all, we could hybridize these orbitals and mix them together. And how would we do that? Leaving out the 1s, 1, 2, 3, and 4. Well, we got to put 1, 2, 3, 4, 5, 6 here. 1, let's put in what we can first. There's 1, 2, 3, 4. Share that, 5, and share that, 6. How would oxygen attain the electron configuration of neon? I would say it's got to make 2 bonds with these. Well, if these are all approximately sp3 hybridized, and they're only very approximately so because all the bonds are not equal, and in fact there's these lone pairs of electrons, well, then we could take an oxygen here like this, could take one like that, put something out here like that, and put out here like that, like that. Let's make a molecule of water, H and H. And what would we have over here? We'd have 2 electrons here, and we'd have 2 electrons here. This is not a perfect tetrahedron because these take up a lot of space and push those together, and this is discussed in the book, and we could talk about that more at another time. But here's a molecule of water. This is H2O. Does the oxygen in here resemble neon? Sure it does. 1, 2, 3, 4, 5, 6, 7, 8, and 2 in the 1s orbital make 10, just like neon. And the hydrogen resembles the electron configuration of helium. 1, 2 for that hydrogen in this bond, and 1, 2 for that hydrogen in that bond. And so you can see where these lone pairs of electrons come from. And you know what? I know I'm not supposed to say max, but I want to tell you this, that it's very important to understand where these lone pairs come from, because lone pairs of electrons are extremely important in understanding the reactivity and the properties of organic molecules. And these lone pairs of electrons don't come from some arbitrary place. They come fundamentally from the electron configuration of the atoms to attain the electron configuration of the noble gas in the second row of the periodic table, which is neon, or the first row, which is helium. And so all of these are trying to be like neon, and from here on, these guys are trying to be like helium, hydrogen's trying to be like helium, and that's what drives all this bonding situation and gives rise to these lone pairs of electrons, which are responsible for a lot of the reactivity characteristics of these molecules. So this is something that I wanted to tell you about here. Now, before I erase this, I want to say one last thing about this. What's the reason for the hybridization? For example, here we had oxygen in its ground state. Yeah? Okay, oxygen was in its ground state. So we forget about the 1s orbital, that's not in the valence shell. Why did we have to hybridize this? Why not just say to have 2 electrons in 2s, 2 electrons in 2px, and just have a bond of hydrogen and water, or whatever is bonded to the oxygen, as in glucose, it's not hydrogen, it's carbon, 2py and 2pz. Why hybridize it at all? Why is it necessary to do that? It was necessary in the carbon situation that we showed over there, but why is it necessary here? Well, this has to do with another characteristic of this. The strength of the bonds and the way the electrons are held in the atom is associated with bringing these electrons in these orbitals as close or overlapping with the coulombic force of the positive nucleus. The s orbital, and I think you learned this in general chemistry or in high school, the s orbital is closest to the nucleus, speaking in that kind of physical way. And so you get the strongest kinds of bonds when you make bonds that have s orbitals as components of that orbital that makes that covalent bond, or s orbital components of the electrons that are held in a lone pair. That's what gives stability to increase that Coulombic interaction, that plus-minus interaction between the nucleus of the atom and the electrons in the orbital. If we left this here, these electrons are fine. They're very much attracted to the positive nucleus. But here you have a lone pair of electrons in 2px, and 2px actually has a node at the nucleus. It doesn't overlap with the nucleus. And not only that, these bonds would be weaker because there'd be no s component to that. By hybridizing these, we give s characteristics to the lone pairs and s characteristics to the oxygen-hydrogen bonds. So what we're trying to do in this bonding of the second row of the periodic table is to get an electron configuration that resembles the noble gas, the filled or empty shell here to be like neon, filled shell to be empty shell to be like helium, filled shell to be like neon, and at the same time to give as much s character to what we're using in order to make strengthened bonds and hold lone pairs in more stable situations. Okay, that's what I want to talk about there. Now I'd like to tell you about something else right now. This is all very, very fundamental stuff, but helps us to understand something about glucose, the three-dimensionality of glucose, how the carbons and the oxygens and the hydrogens are bonded. If you look now at the structure of glucose in the light of what we were just talking about, you would see that every carbon atom has in its electron configuration around it, has a resemblance to neon. Every hydrogen is like helium, resemblance electron configuration to helium. Every oxygen has a resemblance of the electron configuration to neon. The three-dimensionality of the glucose molecule arising from the fact that we are making the bonds by hybridizing the px, py, and pz orbitals into these bonds and into the lone pairs in these bonds, which forces the atom to project its bonding and its lone pairs along the three Cartesian coordinates, which gives us the three-dimensionality. Now, at this point, I'd like to talk to you about something else, which some people don't like this kind of thing, but I think it's very useful to talk about formal charge. It says valence electrons not used for bonding become lone pairs of electrons. Well, I hardly have to go, that's what we just went through. Shown usually by two dots on the atom. Well, that's what we did before. Now, electrons around an atom are counted in two ways. Those that surround the atom and those that belong to the atom. All of this, of course, is discussed in further detail in a historical and storytelling context in the book, which I hope, you know, those that you're using this with the book and you find that, you know, very, very interesting and even entertaining, believe it or not. From this counting, we get the octet rule and the concept of formal charge. Well, the octet rule is just another way of saying that the atoms to the right on the second row of the periodic table, starting with boron and carbon and nitrogen and oxygen and fluorine, are all trying to get 8 electrons around them in order to resemble neon. Well, how's this guy right here? Here's methane. Okay, we're drawing these things in 2 dimensions now for this particular purpose. How many electrons surround that carbon? 2, 4, 6, 8, 2 in each of these bonds, 2 in the 1s orbital, that's not the valence shell that we're not showing, and therefore we have 2, 4, 6, 8, and those 2 down there, that makes 10. This guy, this carbon, looks like the electron configuration. It's not really neon, but it's got the same electrons around it as neon would have. Now there's another way to count these electrons. Really, of these bonds, half of the electron arises from the carbon, and the other electron arises from what the carbon is bonded to, which is hydrogen and methane, which is this particular molecule here. So from the point of view of belonging to the atom, half of that, half of that, half of that. There's only 4 electrons belonging to that carbon, plus the 2 in the 1s orbital that we're not counting here. What's the atomic number of carbon? 6. Half of that, half of that, half of that, and 4, and the 2 in the 1s orbital is 6. The protons in the nucleus are coulombically satisfied, and there's no charge associated with that entity right there. Let's take an oxygen here. Here's an oxygen atom in glucose, or something would be at the ends of that, any oxygen atom in glucose. I just showed you that the oxygen will have 2 lone pairs on it in its normalized state in order to correspond to the electron configuration of neon. Well, you can count them up. 1, 2, 3, 4, and the 2 bonds, 5, 6, 7, 8. 2 in the 1s orbital make 10. Perfect. Here's another way that oxygen bonds. Here's a carbon-oxygen double bond. We're going to talk about this kind of thing, especially in Chapter 3. 1, 2, 3, 4, because the lone pairs belong entirely to the oxygen and surround the oxygen, plus 1, 2, 3, 4 in each of those bonds. 1, 2, 3, 4, 5, 6, 7, 8, and 2 make 10 in the 1s orbital. We've got the electron configuration of a sort of a faux electron configuration of neon. Faux being, how do you spell the French faux? F-A-U-X or something like that? Yeah. And how about this carbon right here? 1, 2, 3, 4, 5, 6, 7, 8, surrounding that carbon. So that carbon also has and 2 in the 1s orbital, the electron configuration of neon. The hydrogens here are also perfectly satisfied, because 1, 2, that's like helium, 1, 2 like helium, so on and so forth, 1, 2 just like helium, and so on and so forth. Now, that's the electrons surrounding the atoms. How about the electrons that actually come from those atoms, that are contributed by those atoms, that belong to those atoms, quote unquote, so to speak, belong? Well, what belongs? Half of that and half of that is 2, 3, 4, 5, 6, right? And what's the atomic number of oxygen is 8. So 1, 2, 3, 4, and half of that is 6, and 2 in the 1s orbital make 8. The protons in the nucleus are perfectly satisfied. What about this carbon? Half of that and half of that, 1, 2, half of that and half of that, 3, 4, and the 2 in the 1s orbital make 6. Perfectly happy. Everything's perfectly happy. Let's jump ahead. And this one you can make sense of by yourself. Let's jump ahead to this one right here, because here's something new is introduced. This is the structure. Let's go to blue here. This is called ammonium. That's called the ammonium ion. All right. Sorry to write that sideways. Like you turn your head. That's the ammonium. You don't have to turn the camera. Whoever's watching this, they can look at it that way. That's the ammonium ion. Well, let's look at this. Is this nitrogen attaining the faux electron configuration, the filled shell of neon? Certainly it does. From the point of view of what surrounds that nitrogen, you've got 1, 2, 3, 4, 5, 6, 7, 8, and 2 in the 1s orbital make 10. And so this nitrogen is very much a filled shell in terms of the electrons that surround it. On the other hand, though, if we count the electrons that actually belong to it, that are contributed by that nitrogen to the bonding, it's only half of each of those bonds. 1, 2, 3, 4, and the 2 in the 1s orbital would make 6, but nitrogen has an atomic number of 7. There are 7 protons in the nucleus of nitrogen. It's only got 6 electrons that belong to it in this case, and therefore this will have a missing electron from that point of view, and therefore a positive charge. And this is the reason why the ammonium ion is positive like that. Well, this is a kind of just to get you familiar with these kind of concepts that we're going to talk about in this book that's written in this historical context, storytelling, top-down manner. Okay, so let's go on now and get back to the nature of glucose, to our popular molecule, glucose. What did I? Didn't I? Oh, here it is. I knew I had to erase something. Let me erase this right here. Now, there are two forms of glucose. Well, yes, there are two forms of glucose. Here they are. The two forms of glucose are so-called alpha D-glucose and beta D-glucose. The alpha and the beta have to do with the direction of this OH, which by the way is called hydroxyl. It's a functional group. We're going to talk more about functional groups in Chapter 2 and in subsequent chapters. There's a whole table of functional groups in the beginning of this book, and functional groups are going to play a big role, but you don't have to memorize them, because the way this top-down approach works is that they come to you as the material develops. Well, this hydroxyl group is pointing downward, is sort of perpendicular to the approximate plane of the ring. This hydroxyl group is pointing approximately parallel to the ring. We're going to talk about this a lot in Chapter 3 when we talk about galactosemia and how the difference between axial and equatorial, we're going to learn what these are called, axial here and equatorial here. We're going to learn what they're called and how they can lead to a deadly disease of infants. We have to wait for Chapter 3 to that. The point that I want to make now is not so much about functional groups and what these are called, but I'd like to know what's the relationship between these two molecules. Well, do they have the same formula? Do they have the same formula, I ask you? Of course they have the same formula. C6H12O6, C6H12O6. If I have two molecules that have the identical formula, then in fact those molecules are called isomers. So molecules that have the same formula are called isomers. I don't care what their structures are. I don't care what they look like. I don't care what I don't care anything about them. If they have the same formula, they're called isomers. And isomers, two molecules that are isomers are very interesting in a way, because experiments can be done that are quite important. For example, if you have two molecules with the identical formula, well then in fact you can compare their thermodynamic energy. It's on the same scale. You can burn them up and see how much CO2 and water you get out, and measure the heat that comes off, and measure their relative stability. You can do all kinds of things in the comparison between two molecules or isomers. So the two forms of glucose are called isomers. Now, what's the difference between them? Do they have different bonding in any way? I don't think so. The bond, yes, their shape is different. Certainly this guy is shaped that way, and that fellow is shaped that way, that's for sure. But are they bonded up in a different way? I don't think so. If you look at all the connections here in alpha glucose and all the connections in beta glucose, you'll find that the connections are identical. Oxygen to carbon to carbon to carbon to carbon to carbon to carbon. Everything is identical. The hydroxyl groups are all, the bonding is identical, but they differ in their shape. If you have two molecules that have identical bonding, that have identical formula, they're isomers. If they have identical bonding but differ in their shape, then they're stereoisomers. And they're stereoisomers because the word stereo corresponds to a three-dimensional difference. So now, isomers like this that are stereoisomers, so these two are stereoisomers. These two are stereoisomers, and they're stereoisomers which differ in their shape. Well, there are other kinds of isomers which don't differ in their shape, or have another kind of a property which has to do with mirror images. There are isomers that are not stereoisomers. There are kinds of isomers called constitutional isomers. What do you mean by constitutional isomer? A constitutional isomer have different kinds of chemical bonds. Let's look at the example of some constitutional isomers. For example, what's the formula here? Well, this is a good way to practice what we learned in the first part here. Carbon, 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 carbon. That's the rule. Have to be 4 bonds. Therefore, 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3. Hydrogen at the end of these lines. hydrogen at the end of these lines. This was the rule that we learned, and the formula for this should be C6H14. Let's check it out. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In a later chapter, we're going to learn the rules of, and I believe in chapter 4, when we're going to talk about how industry makes high-octane fuel, we're going to learn the rules about these formula. But it's not important that you get into that right now. I simply want you to play this game with all three of these. All of them are C6H14. All of these down here are C6H14O. What do we mean by C6H14O? Well, C6, 1, 2, 3, 4, 5, 6. There's the O. How about the number of hydrogens? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. You can put those in yourself. So this is all these three are C6H14. All these three are C6H14O. What's the relationship between any two of these? Because when you talk about isomers, you're always talking about pairwise relationships. It's two molecules that you're comparing. They're isomers or they're not isomers. What's the relationship between these two? Well, they're isomers. What's the relationship between these two? They're isomers. What's the relationship between these two? They're isomers. Are any of these isomers along this line stereoisomers? No. They're not stereoisomers because they have different kinds of bonding. The bonding is completely different. This has got 6 carbons in a row. This has got a carbon with 3 carbons on it. And let's just, here, this is CH3, 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 CH2, and CH3. Clearly, that's bonded up completely different from that, and similarly, that's bonded up completely different from that. So what's the relationship between it? Well, they're certainly isomers. They're not stereoisomers, and their bonding is completely different. Then, in fact, they are called constitutional isomers. So any two isomers, that is molecules, two molecules that have the same formula, but have different bonding relationships within them, are called constitutional isomers. Constitutional isomers have different properties, period. In fact, if constitutional isomers did not have different properties, the fractionation that goes on in the petroleum industry wouldn't be possible, because what is pumped up from the ground, the petroleum pumped up from the ground, is full of molecules that are constitutional isomers, and they can be separated by all kinds of distillation techniques. For example, can you see this clearly? What's that? This boils at what? 69? Is that 69 degrees? Is that correct? And this is 50 degrees, and that's 60. They're all boiling at different temperatures. Here, this is boiling at 159 degrees. This is boiling at 22 or 32 degrees, and that's boiling at 91 degrees. So any two molecules that are constitutional isomers are going to have very different properties, and not only their boiling points, but all their properties will be different. In chapter 2, we'll learn how their spectra will be different, their mass spectra, even their mass spectra, their infrared spectra, their nuclear magnetic spectra. The constitutional isomers are different, period. In fact, they're as different as any two molecules. If I have two molecules that are different molecules, that are different other than just their shape, well then in fact they're going to be different in every way. And two molecules that are constitutional isomers, even though they have the same formula, are different in every way. Well, all of that is very lovely, but what about stereoisomers? Well, in fact there are two kinds of stereoisomers. These two stereoisomers of glucose, alpha glucose and beta glucose, are special kinds of stereoisomers, because two molecules that are stereoisomers can differ in their shape, but sometimes two molecules of stereoisomers don't differ in their shape. Sometimes two molecules of stereoisomers may have identical shapes, but may be non-identical mirror images of each other. And I'm going to show that shortly. Now, if you have two molecules that are stereoisomers which differ in their shape, in other words, they don't differ because of a mirror image relationship, which we're about to get to momentarily, but differ in their shape, as alpha glucose and beta glucose clearly differ in their shape, then they are called diastereomers. And here's the word. Two molecules that are diastereomers, such as the two forms of glucose right here, or two molecules that are constitutional isomers have different properties. Two molecules that are constitutional isomers have different properties, period. You can separate them. One could be a liquid, one could be crystal. All kinds of differences are possible. Two molecules that are stereoisomers, which differ in their shape, are diastereomers, and diastereomers, like constitutional isomers, differ in their properties. Alpha and beta glucose are different from each other in every way, just as these molecules are different from each other in every way. In that sense, constitutional isomers and diastereomers share a property. Two molecules that are constitutional isomers are different, period, and two molecules that are diastereomers differ, period. And that's the way it is. Let's now talk about molecules that are stereoisomers that don't differ in their shape. How could that be possible? Well, let's go on. Let's go on. Let's erase this. So everything is erased here. Very good. Let's look. What do we have here? Here we have the alpha glucose. We just had that on the previous PowerPoint. That's alpha glucose. Here's beta glucose. I told you that these are diastereomers. They're stereoisomers that differ in their shape. And since they're stereoisomers that differ in their shape, we can expect them to have different properties. Well, in fact, the melting point of alpha glucose is 83 degrees C. And the melting point of beta glucose is 150 degrees. That's pretty different. That's a difference of nearly 70 degrees in their melting temperatures. You heat this fellow up here, you heat this molecule up, and by 83 degrees it'll turn to a liquid, and you've got to go nearly 70 degrees higher to melt the beta stereoisomer, the diastereomer. So these molecules here are related to each other as stereoisomers of the variety called diastereomers. Well, similarly, and we'll get to the difference in a second, here's alpha glucose. Isn't this alpha glucose? Look, here's the shape like that. And here's beta glucose is the shape like that. And 83 degrees here, and 150 degrees approximately there. And these are diastereomers, aren't they? Right? Now, here's something interesting. I've drawn this molecule like this. This is alpha glucose. This is alpha glucose here. They have identical melting points, but they differ in another property. First of all, what's the difference between these two? They're both alpha glucose. Are they identical to each other? I don't think so. If I were to pick this up, and this is where I would like you to get a set of models, which is suggested in the book. And I may give you that as a gift after the shooting is all over. If I pick this molecule up, and I obviously can't pick it up and lay it on top of this because the oxygen here would be back there, but I can pick this molecule up. Watch me in your mind's eye. Turn it around. Are you seeing that? I'm going to pick this up and turn it around. Now I can put this carbon with this OH right on top of that carbon with that OH. But when I did that, this oxygen would now be in the front. And that oxygen, I cannot superimpose these two. It's absolutely impossible. Yet they're bonding it. Their formula are identical, isomers. Their shape is identical, stereoisomers. These two molecules are not diastereomers. There's something very different about them. They're not the same, and yet they're not diastereomers. These molecules are related as mirror images, and they are called enantiomers. Well, they seem to have identical melting points. Well, in fact, they have identical properties in all respects, except under certain conditions. And I'm going to explain those conditions to you in a second. But first, I want to point out that the same situation exists for beta glucose. This beta glucose melting at about 150 degrees, and this beta glucose melting, is that 150 or 160? What is that? Is that a 6 or a 5? Huh?
150.
150. these molecules are also mirror images. This symbol, this being representative of a mirror. They have identical melting points. Mirror images are identical in all respects, but they differ under certain conditions. And I would like to explain the conditions where they differ. And the best way to do that, the best way to do that is with a glove. The best way to do that is with a glove. First of all, forget about forget about my wedding ring, forget about my watch. Just forget about the scar that I got swimming in Coney Island when I was a teenager. Just look at my two hands. My two hands are related as mirror images to each other. I have my right hand and I have my left hand. You can't tell the difference between these two unless you present my hands with something which is itself capable of mirror image isomerism. The way to tell mirror images apart is to present each one with something which is itself capable of that identical kind of relationship. And what could be better than a glove? Here's a right-handed glove. If I take this right-handed glove and I put this right-handed glove on my right hand, it fits very nicely. Here it is. Here's my right-handed glove. Now if I take this right-handed glove and I put it on my left hand, in fact I can't put my hand in there in a proper way at all. This glove, being in a mirror image relationship to its handed glove, this right-handed glove, which has a non-identical mirror image to its left-handed glove, one of these gloves can distinguish between my right and my left hand. And so this is the situation with molecules. If I take a molecule which is capable of mirror image isomerism, one molecule, one enantiomer, and I present to it two molecules that are enantiomers of each other, different molecules, then that molecule, which is itself capable of mirror image isomerism, just as that glove is related non-identically to the mirror image glove, that molecule can distinguish between those mirror image molecules. And there's a very interesting, and this is described in the book, of course, in great detail in historical context, how Pasteur came up with the first demonstration of this kind of thing, all this stuff. I strongly recommend that you look at this. This is just an overview here. And in the book it describes, this is called an alpha D. This is called a specific rotation. And here you'll notice that the specific rotation of alpha D glucose, this is alpha D glucose, we'll talk more about that in chapter 3, is plus 112.2 degrees. And here alpha D is minus 112.2 degrees. Where do these numbers come from? Well, in fact, there's a form of light called circularly polarized light. There's a form of light where I can take light that is circularly polarized. So the light will approach the molecule, perhaps in solution, by turning in this way, in a right-handed spiral. And another form of that light can turn in a left-handed spiral passing through the molecule. Now, because these two forms of light are mirror image related to each other, they cannot be distinguished except by an entity which is itself capable of mirror image isomerism, just like that glove. So let's let this molecule, the alpha D glucose, play the role of the glove. Okay? Let it play the role of the glove, and I'm going to approach this molecule, which is playing the role of the glove, with the left circularly polarized light and the right circularly polarized light in an experiment in a device called a polarimeter. And because this molecule is capable of mirror image isomerism, it will distinguish between these two, and the index of refraction of the left and right circularly polarized light will differ as the light passes through this equivalent, what's doing the equivalent job that the glove did for my hands. And when it does that, the index of refraction differs. The plane of the polarization of that light will shift, and the shift of that plane of the polarization is represented by that number. And if we do that experiment with this particular glucose, it'll shift in a way that's given a positive number. And if we do the identical experiment with the enantiomer of the alpha glucose, the index of refraction will change in the other direction, and and the plane of polarization will go one way, and this way it'll go the other way. And this is just the beginning of the way to distinguish between mirror image molecules, and much more about this is discussed in the book, but I just wanted to give you an overview of what is going on here. Now, let's erase this. There's an interesting history behind this, and for a long time there was no way to name mirror image molecules. You could say, well, I had one form of glucose and the other, and I said, which one do you have? You could draw a picture of it. Or you could have a molecule that's capable of mirror image isomerism, and you wouldn't know how to name it. And it would be difficult to do that. And it's described in the book how this was first solved by three European gentlemen, Kahn, Ingold, and Prelog, who are talked about in detail in the book and the history behind it and all that kind of stuff. And they said, look, there's a very simple way to name this. If we have a molecule that's chiral, and now I'm introducing a new word to you. What do I mean by the word chiral? Well, chiral comes from the Greek word for hand. If I have two molecules that are mirror image related to each other, then they differ as our hands differ from each other, and so they're called chiral molecules. This molecule is chiral. And a chiral molecule in general, in its simplest form, could be represented by a carbon atom. And let's draw this in 3 dimensions like that. And let's say we have a carbon atom with a hydrogen here, and something here, and something here, and something there. Well, what do these represent? These don't represent atoms. These are symbolic for different entities. There's something different here, and different here, and a hydrogen here. And if you like, this doesn't even have to be a hydrogen here. It could be just something like that. In other words, if I've got a carbon with 4 different entities around it, then I have a carbon, then I have a molecule which is chiral. As soon as you have a molecule with 4 different entities around it, I guarantee you that it will be not superimposable with its mirror image. In other words, it will exist in enantiomeric forms. That's the fact about this kind of molecule. And they wanted to come up with a way to name this, and the history behind this is fascinating about how the synchronicity of time and how the naming of this became important. And it's something I don't want to spend gigabytes on this right now, but I want to show you what they came up with. It's so simple, it's amazing that no one thought about it before. Here's a molecule with 4 different groups around it, right? CH2OH is certainly different from OH. It's certainly different from a carbon with a double bond to oxygen. It's certainly different from hydrogen. So here's a carbon right here, which we draw here in black, which has 4 groups around it. I guarantee you it's non-superimposable with this mirror image. Can we name it in some way? Well, if we know the overall structure, we know how things are bonding up. Kahn, Ingold, and Prelog pointed out a very interesting way to do this. Let's take the atomic weight of each of the 4 different entities. Which is the highest atomic weight? Well, I would say OH is the highest. That oxygen has the highest atomic weight. Oxygen has a higher atomic weight than carbon, so we give this 1. Then we have here carbon is attached and carbon, because here's a carbon too, right? There's a carbon right there also. So which of these gets priority? This carbon here or that carbon here? Well, then we look beyond what's directly attached. This carbon is attached to 2 hydrogens and an oxygen. This carbon is attached to only 1 hydrogen and the equivalent of 2 oxygens, because you've got a double bond, so you count that as 2 oxygens. Therefore, this carbon has a higher priority. It's got a higher effective atomic weight. So we go for 1, and we go here to 2, and what would be 3? Well, 3 would be the other carbon, and hydrogen would certainly be 4, because it's got the lowest atomic weight. Well, all of that's very nice. Then they said, look, here's, I don't know if this is clear, but put your eyeball here. Here's your eye, and look at that carbon with the 4th group, the hydrogen in this particular case, facing away from you, as if you were looking at the face of a clock. Just like you're looking at the face of a clock, and the hydrogen in the back, the lowest priority group, is like the wind-up of the clock in the back. And now we go 1 to 2 to 3. We come out here, we go back in, and we go around here like that. In other words, we're out here, we come in the plane, and then we go back behind the plane. That is a clock turning in the normal direction. That's clockwise, and therefore we call this R. And you can play that game with any of these entities right here. And histidine and serine are amino acids, and lactic acid is a biological entity, and malic acid is a very important biological entity. And many biological molecules, in fact almost all biological molecules, have this chiral characteristic. And as we're going to see, this chiral characteristic is also associated with enzymes and the shape of enzymes. It's a wildly important aspect of understanding the nature of biochemistry. We're going to talk about it in the citric acid cycle later in the video series, and in the book it's a theme that comes up again and again, and here we're just being introduced to this particular. Let's take lactic acid right here. Here's natural lactic acid, which is going to be 1. Well, that's going to be 1 right there because that's an oxygen, which is going to be 2. Well, although that's a carbon and that's a carbon with the equivalent of 2 oxygens on it, with 3 oxygens on it, 2 to the 2 lines, the double bond, and 1 here, and this is certainly going to be 3, and the hydrogen in the back is going to be 4. So if I go here 1, 2, 3, then I'm going and looking at the clock that way. That's clearly S, which is counterclockwise. And so this is the nomenclature of this kind of thing. Now, there's something I want to say about this, which is talked about in detail in the book. If we go back, I want to go back for a second. I want to go back for a second. And this is something that you may have noticed back in the first PowerPoint. This is called D-alpha glucose. This is called D-beta glucose. This is called L-alpha glucose. And this is called L-beta glucose. The difference, let me get the blue marker for a second. The difference, the alpha-beta difference, is the diastereomeric difference. That's the diastereomeric difference. That's the alpha or the beta. That's the symbol that corresponded to the different shape of these sugars, and that's the diastereomeric difference. Now let's get the red marker here. The D, though, and the L here, which is the same as the L and the D symbolism right here, correspond to, the D and L correspond to the enantiomeric difference. These symbols, D and L, we're going to talk about in Chapter 3 in detail when we talk about galactosemia. We go back and see what Emil Fischer did. These are symbols which were arbitrarily given to these sugars when the structures in stereochemistry were first figured out in the early part, very early part of the 20th century. So the red circled, the capital D and the capital L correspond to enantiomeric properties, and the alpha and the beta correspond to diastereomeric properties. And I hope you look further into this. Let's go on. Molecules are in constant motion. It's kind of hot in this room right now. And the heat in this room is felt by the molecules that are bouncing off our bodies, coming off that light, that bright light that's lighting up what we're doing right here. The oxygen and the nitrogen and other entities in the air are deriving translational energy from those molecules. The molecules are moving at thousands of miles an hour, and the faster they move through the air, the faster they impinge on us or on the earth around us, the warmer we and the earth will be. Global warming is related to that. It's the carbon dioxide absorbing the sun's energy and moving faster and faster and causing a heating up of everything. Well, that's translational motion. Okay, very good. So molecules can translate. Are you with me? Like, see, in other words, any molecule is moving like that, changing their position in space. But molecules are doing other things too. They're not only undergoing translational motion, they're also undergoing vibrational motion. What does that mean? Well, if my fists are carbon atoms and they're connected by a covalent bond, they're constantly in vibrational motion like that. And in fact, that vibrational motion is the foundation of infrared spectrometry, which we're going to study about in Chapter 2. So you can have molecules moving, you can have molecules vibrating. A different kind of motion is an angular motion. Let's say we have a carbon atom here at the base of my thumb and my finger, and that angle is constantly changing. That's called angular motion. So I can have translational motion, vibrational motion, angular motion, and there's another kind of motion also called rotational motion. And rotational motion is what I want to talk about right away. So one molecule is represented, shows one kind of motion, rotational motion. That is the twisting around the single bonds of atoms. Let's take the black marker and do that for a second. Let's take a molecule called ethane, all right? Ethane. We've already seen methane, haven't we? Right? Here was methane. See? And by the way, we now know that the tetrahedral arrangement around methane is approximate because the angles here are constantly changing. So only on average does it have a tetrahedral relationship. Let's take ethane. So methane is CH4 and ethane is C2H6. Okay? C2H6, CH3, CH3. Let's draw that another way. H, 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 C, H, H, H. Is that correct? No, it's got to be in 3 dimensions. So how are we going to make it in 3 dimensions? Well, let's draw it as a sawhorse projection. That's a common way that we represent the 3-dimensionality of these molecules. Well, you remember when you were a kid? Here's a sawhorse, right? You sat on the sawhorse and you held on here, and that was the tail over there. Hydrogen, 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 hydrogen. The long lines are coming out towards you. Is that clear? Is that perfectly clear? The long lines are coming out towards you. The short lines are going in the back, and these lines are in the plane of the whiteboard. So this is ethane. Okay, very nice. Now, here's a bond. This covalent bond connects these 2 carbon atoms. That covalent bond has a cylindrical symmetry. That has a cylindrical symmetry. In other words, it has the characteristic of a cylinder. Well, if I've got a cylinder, you know, for example, this entity right here, like this, between my hands, take off that end and take off that end, and forget about all the writing on it. I can turn it around and there's no difference. Of course there's a difference here because there's writing on it, but if there were no writing on it, there'd be no difference whatsoever. I can rotate around a cylinder without consequence. Well, this has therefore that possibility. Let's not use black for this because then it'll get mixed up. Let's take this away here. I can rotate around that cylinder, and pretty much it used to be called, it's not exactly free rotation, but it used to be called a kind of a free rotation. So let's rotate around that cylinder. Well, if we rotate around this cylinder, there's no consequence to that. Well, in fact, if I rotate around the cylinder that connects the carbon and the hydrogen bond. Here, there's no consequence of that because the hydrogen is spherically symmetrical, so you don't see anything. But if I rotate around this cylindrically symmetrical bond, covalent bond between that carbon and that carbon, then in fact, which is called, by the way, a sigma bond, the symbol sigma, and we're going to go into that in the book later and in more detail. All of this in more detail in the book. If I rotate around this, there's going to be a consequence of that. What's the consequence of it? Well, in fact, if I move like this, if I leave the front alone and I rotate that around like that, hydrogen, 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 this stays the same, and I rotate that around and I take this hydrogen and bring it down there, then in fact I'm going to take this hydrogen and put it in the back and that hydrogen and put it in the front. Now this motion is called conformational motion. That's called conformational motion, and these entities, I'm going to call this A and I'm going to call that B. A and B are conformational isomers. Isomers? Why are they isomers? Well, of course they're isomers. The two entities A and B, they have identical connections, so they're clearly isomers. What kind of isomers are they? Well, what kind of isomers are they? They're clearly what? They're clearly stereoisomers, right? They're clearly stereoisomers because they differ in their shape, don't they? Are they mirror images of each other? Well, if they're stereoisomers and they're not mirror images of each other, then what kind of stereoisomers are they? They have to be what? They have to be diastereomers. So therefore, we're discovering now that because of the rotational motion possible in a molecule like ethane and many other molecules, as we're going to see shortly, you can have the molecule take different, you can have the overall molecule, and because of rotational motion around the bonds, the molecule can take a variety of different shapes. And here's two shapes that ethane can take. This is a shape that is called, this is a shape that's called eclipsed. Why is this called eclipsed? Well, this is called eclipsed because all the bonds are right behind each other. Everything is eclipsed. It's like the sun and the moon are eclipsed. Everything is eclipsed here. This is called, on the other hand, anti, or sometimes trans, but anti. Why is this called anti? Because now, instead of everything eclipsed, these are opposite from each other. Well, these are diastereomeric conformational motion that causes these conformational isomers to appear. What's going on here? Well, in fact, what's going on here, and let's do this in green, this double arrow means that these two are convertible with each other. And because they're conformational motion, that motion is convertible on the ballpark of 10 to the minus sixth of a second or shorter, or faster than that. In other words, these only exist momentarily before they go back and forth to each other, and it's impossible to isolate one from the other. If we had, and you and I have talked about this, if we had Maxwell's demon, which you can look up on Google, which I know you've done already, then in fact we could say to Maxwell's demon, would you do me a favor and stop time for a moment, which is impossible, and isolate that, and put them in different bottles, and if we burn them up and to CO2 and water and measure the heat that came off, we'd find that we get more heat out of that one than we get out of that one, because that's more unstable than this one is. And the instability comes from something that you can imagine. Remember the source of the tetrahedral array, to keep those electrons and those bonds as far away from each other as to keep these electrons away from these and these electrons away from these. Well, the eclipsing of these bonds is a repulsive force, and that repulsive force, and we're going to talk a great deal about that in chapter 3, is called torsional strain. So conformational isomers can differ from each other in different ways energetically, and one of the ways they can differ from each other is through something called torsional strain. There's other ways too, but we're going to save that for chapter 3 when we talk about the disease, the malady of infants called galactosemia, and what that has to do with these kinds of ideas. So this is a very rapid type of a situation. Now I'd like to erase this right now because I'd like to show you something. Let's take these conformational isomers, diastereomers, rapidly into converting. There was a gentleman who I met once, a very interesting organic chemist, a very good man who did a lot of stuff. His name was Melvin Newman. His picture is shown in the book, and there's some interesting stories told about him, about some funny incidents that happened. Newman said, look, there's a nice way to represent these other than these sawhorse projections, and he didn't give his name to it, but people came to call it after him, called Newman projections. Let's say, take away the A here, and put our eyeball down here. Put our eyeball down here. Newman suggested make a circle. The center of that circle is that carbon. There's a hydrogen here, a hydrogen here, and a hydrogen here. And now behind that carbon is another carbon that you can't see. There's a hydrogen behind, a hydrogen behind, and a hydrogen behind. So these two here, excuse me, these two right here, which we circle in blue, are these right here circled in blue. This is called a Newman projection. These are what it's called. And here we can see that we have an eclipsed conformation. And there's a rapid motion taking place here, which can be represented by, and this is the generally best way to do this, leave the front one the same, rotate the back one, hydrogen, hydrogen, hydrogen. So now we go from an eclipse conformation to this anti between the two hydrogens, and these are now no longer eclipsed. Nothing is eclipsed with each other. This is the more stable conformational diastereomer. So these Newman projections are widely used in organic chemistry. Many molecules are represented with Newman projections. Newman projections are often used to show conformational motion, named after Melvin Newman. Let's go back here, over here. Can you see me over here? Or is it too dark on this side? No, I can see it. Okay. So we just went over an idea. One way molecules are represented shows one kind of motion, rotational motion. That is twisting around the single bonds between atoms. Let's take a molecule. Here's a molecule called mesotartaric acid. We're going to talk about that. In fact, a derivative, a salt of tartaric acid, was how Pasteur discovered some fundamental principles of stereochemistry that are fascinating to learn about, in my opinion. And you can see his picture and talked about all this in the book. Now, here's mesotartaric represented in a way that I did not represent anything over there. Here we can take this over. I didn't represent anything over there. If I take this so-called mesotartaric acid and I pick it up and turn it over, see, and let this group be represented by simply CO2H. Let these groups be simply represented by CO2H and not designate their bonding. We're going to go into their bonding later in the term, or later in the reading of this book. If I simply take this and turn it over, see, this is not a rotational motion now at all. I'm simply taking the whole molecule and turning it over, just like I'm taking my hand and turning it over. I'm not moving any atoms with respect to other atoms in the molecule. I'm just taking the whole molecule, turn it over. If I take this whole molecule and turn it over, then the CO2H groups come up the top here, and the OH groups, which were in the front, are now in the back, and the hydrogens, which were in the back, are now in the front. That will call that structure. So it says right here that 1 and 2 are the same. They are. I just took that and turned it over. That's a kind of a translational motion. As molecules are flying around, you know, they're turning and twisting in every which way, and this is one of those ways. But this is not a conformational. This is not a motion around the bond. This is not a conformational motion. Now, let's take this molecule, pick up 2. Let's pick up 2. See, here's 2, right? And what are we going to do with 2? We're going to take 2 and turn it that way. See what I'm doing? Again, this is not a conformational motion. I'm simply taking 2 and I'm turning it that way. What happens when I take 2 and I turn it that way? Well, the CO2H group now comes out to the front. This CO2H group comes out to the front. And when that comes out to the front, the OH groups come out to the back, and the hydrogens, I'm sorry, the CO2H groups come out to the front, and the hydrogen goes to the back, and the OH groups go up. So I've turned this 2, and it's become 3. So these are all not conformational motions. They're simply picking up the molecule and turning it around to look at it in different ways. And learning how to look at these molecules in different ways is important to learning the foundations to help you project your knowledge into organic chemistry. Now, what's that? Well, like that's a Sawhorse projection. 2 and 3 are identical. And this is a Sawhorse projection. Let's take Melvin Newman's, let's take Professor Newman's idea and present this as the projection he suggested, which people have come to call a Newman projection. He taught at Ohio State University, by the way. So what are we going to do? Here's our eyeball looking down here. And let me come over here. Here's our eyeball looking down here. And when we look down there, what do we see? Well, we see the CO2H out this way. We see the hydrogen back that way and the OH back that way because we're looking at it this way. Can you see that? Is that straightforward? CO2H, H, and OH. That's the front carbon. The carbon in the back can't be seen. The OH in the back is eclipsed with the OH in the front. The CO2H in the back is eclipsed with the CO2H in the front, and the 2 hydrogens are eclipsed with the OH. That's the way that is. Now, can I change the conformation of this? Of course I can. I got a perfect right to do that. I can leave, and in fact the molecule is doing that all the time. I leave the carbon alone, OH, CO2H and H, OH, CO2H and H. Everything's the same. I'm now going to rotate around this bond, and I'm going to rotate in that direction around that center bond. And when I do that, I take that CO2H and I put it up here. I put the hydrogen out front, and I put the OH in the back. That's what I did by rotating around that bond and leaving that alone. And and that's represented right here. CO2H on top, hydrogen in the front, OH goes in the back, and I can represent that by a Newman projection. This is still an eclipsed conformation, but now different entities are eclipsed. Now I've got the OH in the front eclipsed with the CO2H in the back, so-called carboxylic acid. We're going to learn about these as we go. And now the CO2H in the front is eclipsed with the hydrogen in the back, and the OH and the H and the OH. Now I want to ask you a question. What's the relationship between, 3 and 5 are the same. What are these called? 4? What's that, a 6? I can hardly see that. Yeah. 3 and 5, and 3 is the same as 4, just represented Sawhorse, Newman. 5 and 6 are the same, just represented Sawhorse, Newman. What's the difference between these or these two? Or what's the difference between these two? It doesn't matter. The difference between these two is the same as the difference between these two, because the molecules are the same. It's just represented in different ways. Well, these are clearly stereoisomers. They differ in their shape. They're clearly isomers. They are diastereomers. They're both eclipsed conformations, but they're eclipsed in different ways, so they're diastereomers. Now what? Now I can take this. Are you still with me? And now I'm going to take take this and rotate it around that way, and pull this hydrogen down here like that. See, I'm pulling that. I'm leaving that alone. Pulling that hydrogen down here like that. I can do anything I want with this. Pull it. It's happening all the time, like a pinwheel in the wind, turning around. And pulling that down here like that. When I did that, what happened? Well, the OH went to the back and the CO2H went to the front. So that's the Sawhorse projection, represented here by this Newman projection. Again, the OH, CO2H in the front, are remaining the same. We don't change these though, just for simplicity of representational purposes. But now we've seen that as we eyeball down here, the back OH is out here, the CO2H that's coming out to the front is over here, and the hydrogen is down the back. Now we suddenly have an anti-conformation. See that? That's an anti-conformation now. And this conformation will also be, so these two are diastereomers, these two are diastereomers, these two are diastereomers, and they're all in rapid motion, happening millions of times a second. That's the conformational property of these kinds of molecules. And we can make all kinds of, and the more complicated the molecule, the more rotation you can have around this. And by the way, if you wanted to play a game, you could name these RRS too, and you would discover something about the meso concept associated with chirality, which is discussed in the book, and we'll spare the gigabytes by going into that right now, because I think that we are finished with Chapter 1.